Hello, welcome to the third class of the life of stars, and today we will talk about how stars form in nebulae. As we have already seen, the interstellar medium contains particles that originate from many different events. Most of the interstellar gas and dust was produced by the death of older stars. By the way, it's interesting to note that we don't think of stars as transient objects. After all, constellations don't change perceptibly during our lifetime. And stellar events on human timescales are quite rare. But still, we know that stars are born, evolve, and eventually have an end. We already saw that stars form within clusters of gas and interstellar dust in nebulae. These regions are generally extremely cold, with temperatures between 10 and 20 Kelvin, just above absolute zero. In degrees Celsius, it's roughly minus 250 degrees Celsius. And at these very low temperatures, gases become molecular. That is, atoms come together. Carbon monoxide and molecular hydrogen are the most common molecules in interstellar gas clouds. Furthermore, this deep cold causes the gas to accumulate at high densities. And when the density reaches a certain point, matter cores begin to form. All this occurs as a result of a physical process. When matter accumulates, its density also increases and the matter will begin to heat up. In fact, the outer edge of such a cluster of matter will have a temperature of approximately minus 263 degrees Celsius, and the inner region will slowly warm up to 26 degrees Celsius, which is approximately room temperature. Notice this great difference in temperatures between the outer edge and the inner part of this cluster. But now, to continue with the explanation of how a star forms after the collapse of material in the cloud, it is necessary to understand two concepts: kinetic energy and potential energy. Kinetic energy is the energy an object has due to its motion. As long as an object moves at the same speed, it will maintain the same kinetic energy. For example, if we throw a baseball, the ball moves due to kinetic energy. Moving water and wind are also examples of kinetic energy. Or a cyclist riding their bicycle up a hill is also using kinetic energy. In short, the energy of motion. The kinetic energy of an object is calculated from its speed and mass. On the other hand, potential energy is the energy stored in an object due to its position or state. For example, the same cyclist at the top of the hill will have stored energy due to their height above the ground, and then that energy will be released when they go down. Okay, but is this potential energy released and lost? No. We must remember a very important principle in physics, the conservation of energy. For example, a child standing on the roof of a building has a ball that he wants to throw downwards. From the height at which he is standing above the ground, there is potential energy accumulated. But once the child throws the ball, that potential energy is released and transformed into kinetic energy, which is the energy of the ball's motion. Let's keep these two concepts in mind as we will use them throughout the class. They are fundamental in the process of explaining the formation of a star. Returning to the nebula, once the region of the nebula has collapsed to reach a size of 1 trillion kilometers, it is called a prestellar core and is officially a potential star. Stellar means star, so prestellar means before becoming a star. The word core refers to the gas and dust, which are now so dense that the term core is much more precise than the term region or cloud. This prestellar core will later become the core of the future star. Once several prestellar cores have formed through the cloud, each core will acquire its own gravitational force due to the increase in its mass. And as the prestellar core forms, the loose gas begins to fall towards its center. This falling gas releases kinetic energy, that is, the energy of the movement of matter in the form of heat. Thus, the pressure and temperature at the center of the prestellar core will increase, and as its temperature reaches thousands of degrees Celsius, the prestellar core begins to emit more and more radiation to the point that it becomes possible to observe it with telescopes, specifically in the infrared frequency. Very well then, now what will happen with this prestellar core? Will its temperature continue to increase? Will it keep growing? But above all, how will it manage to remain completely stable until it finally forms a star? We will answer these and many other questions in the next module on protostars. See you in the next video. Portair.